In several previous lectures, you may have found that analysis of second-order circuit is much more complex than the first-order circuit. In the analysis of first-order circuit, we have introduced the three elements method, which simplifies the mathematical process and emphasizes the physical background. In this lecture, we will continue such a journey. The analysis of the second-order circuit will be simplified to the analysis of several small resistive circuits. You will fall in love with the process. We call the method intuitive method for second-order circuits. Here, intuitive method refers to not only the direct method for simple second-order circuits, but also includes the method which is similar to the three-elements method for the first-order circuits. By using the state equation and output equations, we solve a series of resistive circuits and eventually get the solution by any branch variable in the second-order circuit, and even includes the qualitative drawing waveform. Let's begin. We first do a relatively simple problem. Look at this circuit. The voltage source and 550 ohm resistor are in series and connect in parallel with a 0.5 Henry inductor and 100 microfarad capacitor. We already know that the initial value of the inductor current is 2 ampere and the initial value of the capacitor voltage is 0 volts. Now the voltage flowing through the resistor needs to be found. We have many kinds of approaches. The first is that we can list the second-order ODE about IR, find the initial value of IR and first-order derivation. You may try it. I'm sure it's not easy to list the second-order equation about IR. The second method, we might as well list the second-order linear ODE with constant coefficient about UC and IL. After find out the UC or IL, by using the element constraints KC and KVL, we can get the expression of IR. This method is relatively simple than the former one, but it's also troublesome. Here we introduce a more intuitive method. In the previous lecture, you should have such an impression. For a dynamic circuit, the ZIR, ZSR, and full response has the same speed of change. That is to say, if you want to know whether any second-order circuit is overdamping, critical damping, underdamping, or no damping, which kind of it, we only need to look at its zero input state. Having this very important idea, we draw its zero input circuit. It's like this. Look, this is the RLC parallel circuit. We have discussed it in the last lecture. The characteristic equation of RLC parallel circuit is like this. Lambda squared plus 1 over RC times lambda plus 1 over LC equals 0. Substituting the value of RLC, we know that it is 200 and it is 20,000. With simple method, we know that it can be written as this form. So naturally, the characteristic roots are a pair of conjugate complex roots. That is, lambda 1, 2 equals minus 100 plus minus J100. It determined that in the circuit, any branch variable changes with the form of underdamping. Because the real part of the conjugate complex is minus 100, so the transient process will tend to be 0 at time as time tends to be infinite. So we can write that the general expression of IR must be the steady state value of IR plus K times e to the power of minus 100t times sine 100t plus theta, where K and theta are underdetermined coefficients. Next, we solve the steady state value of IR. For DC excitation, the steady state of the inductor is a short circuit, and the steady state of the capacitor is an open circuit. So we can draw the steady state equivalent circuit like this. It's easy to get the steady state value of IR as 1 ampere. So the value is 1. Next, we find the initial value. According to the law of switching we learned before, we can draw the 0 plus circuit. It should be noted that it is also a resistive circuit. In the resistive circuit, every inductor is replaced with a current source, and the value of the current source is 0 plus value. Every capacitor replaced with a voltage source, its value is a 0 plus value of voltage. So we draw the 0 plus circuit. Because the 0 minus value of the inductor current is 2 ampere, so here is a current source of 2 ampere. Because the 0 minus value of the capacitor voltage is 0 volts, so this is a voltage source of 0 volts. That is a short circuit line. So we want to find IR in the circuit. Obviously, we need to use KVL in such a loop. Therefore, IR 0 plus equals 50 over 50 equals 1 ampere. In addition to IR 0 plus, we also need to find dir dt at t times equal 0 plus. Do you still remember in lecture 55 how to find out the value of duc over dt at time t equals 0 plus? This is easy there because duc over dt equals 1 over c times ic. By solving the 0 plus circuit, we can get ic 0 plus and accordingly get duc over dt t equals 0 plus. This idea actually can also help us to find dir dt t equals to 0 plus. That is to say, if we can use UC and IL to represent IR, then dir over dt can be expressed as a combination of duc over dt and dIL over dt. Specifically, it's like this. We might as well draw equivalent circuit after switching, where the capacitor has replaced with a voltage source and the inductor has been replaced with a current source. We need to know that IL, UC are unknown variables, but no matter how they change over time, they can all be replaced with current source and a voltage source. In such a circuit, we can write that IL equals 50 minus UC over 50. Because we use a KVL here with the Ohm's law, we can know. So we can find its derivation, that is dir over dt equals minus 1 over 50 times duc over dt. So it is equal to minus 1 over 50 ic. That is to say, we need to go back to the previous 0 plus circuit and find the 0 plus value of ic. We use a KCL here conveniently. We can know it's 1 ampere and it's 2 ampere. Therefore, the 0 plus value of ic is equal to 1 ampere. So we know dir over dt t time equals to 0 plus equals 200 ampere per second. For such a general solution expression, we can use two conditions. That is, IR 0 plus equals 1 ampere and dir over dt t equals 0 plus equals 200. To find out that K equals 2 and theta equals to 0. So we finish the solution of the whole circuit. Please see, with this kind of solving method, we only need its zero input circuit. If it's a RLC serial or parallel circuit, then its response form of any branch variable can be written conveniently. Next, by solving a series of resistive circuits, we can find any branch variable. It's a very convenient process, but it's not general. For such a circuit, if we want to find the ZSR or IR, we use the previous idea and draw the zero input circuit of the whole circuit. That is, this is not a simple RLC serial or RLC parallel, so we don't know its characteristic equation and the form of characteristic roots. So how do we solve the circuit? Do we need to go back directly to list the second order linear differential equation with a constant coefficients about IR? No. In the following videos, we will tell you more simple and more general method.